Hello and welcome to lecture 28 on the topic of relativity. We've moved on to modern physics in our exploration of physics, and this is our first lecture on the topic of relativity. When I talk about relativity, I'm talking about special relativity, which is a specific theory that was postulated by Einstein. There is also general relativity, which will not be covered. But over the next three lectures, lectures 28, 29, and 30, I will be talking about special relativity. So here we just want to introduce what it is, talk about the postulates that led to it, and look at one of its first consequences, which is the concept of simultaneity not being absolute, but instead being relative. So it all begins with this title here, Invariance of Physical Laws. This is an idea that we're going to unpack down below in the key terms. And the other topic, relativity of simultaneity, which follows from the first one. What are our two objectives? Well, we want to learn the two postulates of Einstein's theory of special relativity in the context of history, the history of physics, briefly speaking on the history side. We want to understand why different observers can disagree about whether two events are simultaneous, but will never disagree whether either event occurred. Okay, so we definitely want to establish what an event is and why they would never disagree that it occurred, although that's the part that makes sense. The fact that they can disagree about whether two events happen at the same time or not, that is strange and not something that we see in classical physics or in our everyday lives. So let's take a look at the key terms. We'll review what Galilean relativity is, something you've heard of before, but maybe not exactly by this name. Then talk about an experiment that motivated special relativity, and then actually get into the postulates of special relativity, Einstein's first and second postulate. So what is Galilean relativity? Well, this is really just another name for classical relativity, which is the study of relative motion preceding Einstein, because up to that point, we had the concept that there could be different reference frames. Those reference frames could be moving relative to each other, and the effect would be a relative velocity equation like this, which is a vector equation. Right? So for example, if this is v a with respect to b, because we would read that subscript ab as a with respect to b, that could be equal to the sum of these other two vectors, v a with respect to c, so that could be this vector, for example, and then vc with respect to b would be this vector here. So we can see we have a vector sum, and we have a relative reference frame, c, that's shared by these two relative velocities. And these are the types of velocity equations that would apply to airplanes moving through air that itself is blowing relative to the ground, or a boat moving through water that itself has a current relative to the seabed underneath. Okay, so that's the idea of a relative velocity problem. Now, I also want to talk about the notation, because this is the notation I use and have used in previous lectures in the classical mechanics realm. But we're going to use some different notation here when we talk about special relativity and modern physics. And I want to introduce that, although I'll be showing it more in lecture 29. Okay, so this equation here just shows the velocity. This is the velocity measured by an observer at rest. Then we have the velocity measured by an observer in a moving reference frame. Okay, so like on that boat that's moving relative to the ground, for example. Okay, and then we actually have the velocity of the reference frame itself. Okay, so if we continue with this analogy with boats, then we could say that this is v of the boat relative to the ground. V prime is the boat relative to the water. And the water is what we call our moving reference frame. And a reference frame is just a location where measurements are made. And we're using the letter u, which would be the velocity of the water relative to the ground, like the sea current. Okay, so you see there, u is the reference frame motion itself relative to something that's at rest, and then v prime would be something else moving relative to the moving reference frame. Okay, so the only real key difference is not using the subscripts, using prime and the letter u always for the moving reference frame. Okay, and the name actually that we'll always give that moving reference frame will be s prime. But again, that's really getting ahead of the material. We'll see that extensively in lecture 29. So let's get back to our key terms. Okay, So Galilean relativity, I think you have a good idea what it means. And it essentially states that all velocities are relative to the location, reference frame, in which they are measured. Okay? So that does beg the question, is there one absolute rest reference frame? And it was shown at the turn of the 19th century to the 20th century that that was not the case. And the Michelson-Morley experiment is a famous experiment that showed that there is no absolute reference frame. In other words, it is an experiment that proved that light does not require a medium through which to propagate. And you may be saying to yourself, hold up, what does proving there is no such thing as an absolute rest reference frame have to do with light not requiring a medium? Well, that medium through which light could have been propagating, based on theories that predated the Michelson-Morley experiment, that medium would have been the absolute reference frame. All right, this would have been an absolute rest reference frame. But since the experiment showed that that's not the case, that no such reference frame exists, and by the way, the name of that proposed absolute rest reference frame would have been the ether, right? But it turns out that it does not exist because it was shown that light did not travel at different rates regardless or depending on Earth's motion. All right, so essentially, if you consider laser light in one direction, all right, laser light in another direction, right, that's just the velocity of the light, and then you consider the planet Earth moving in a direction relative to one of the laser lights, well, there is no effect if the laser light was shined parallel to the motion of Earth or perpendicular. And that proved that an absolute reference frame, in other words, the ether, did not exist. That seems like an interesting experiment, but it may seem tangential to this topic of relativity. But it is not at all, in fact, because proving that there was no absolute reference frame begged the question then, what is light, and how does light mesh up or reconcile with other ideas of the universal nature of physics? So let me explain that or expand on that further with Einstein's first postulate, okay? Because it will directly address that question. What is light, and how does light reconcile with our ideas of physics? Because what are our ideas of physics? What are the underlying assumptions of physics? Well, if you think about it, physics should apply, so the laws of physics should be the same in any inertial reference frame. And in fact, they really should be the same in any reference frame. Because by the way, if you don't recall what inertial means, it means constant velocity, which is, in other words, zero acceleration. Okay, no acceleration. So that means straight line motion, you can't turn because turning is a form of acceleration, but any straight line motion at constant speed is an inertial reference frame. And the laws of physics should apply to all of those reference frames, okay? And if we are talking about non-inertial reference frames, those are the ones that include acceleration, well, that's general relativity, which is not covered here in this lecture series, okay? So we will not be talking about general relativity, so we'll only focus on those constant velocity inertial reference frames. But again, back to the basic assumption of physics, the laws should be universal. We shouldn't have some laws of physics that apply to some reference frames and others that don't, okay? So one way to state that, this idea that the laws should be universal, and a very interesting way to state it is the following. There is no experiment, mechanical, electromagnetic, or otherwise, that can be performed entirely in one reference frame that will tell you the relative velocity of that reference frame. So the relative velocity to other reference frames. And again, it's to other reference frames, not to any one special reference frame, because there is no such thing as a one special reference frame, as the Michelson-Morley experiment showed. Okay? So what's another way of saying that? Well, if you are in a room with no windows, you can't tell if that room is at rest or if that room is moving at some speed. All right? You can't tell. There's no experiment you can perform inside that windowless room that will tell you how fast you're moving. You can't swing a pendulum to tell you your velocity. You can't do an experiment with circuits or an experiment with magnets and induction. No experiment will tell you your relative velocity. because there's no absolute measurement to make the relative velocity to. There's no law of physics that points you to some absolute rest. Okay? So if that's the case, and importantly, that whole set of experiments under the umbrella of physics includes electromagnetic experiments, that means light must behave the same in every reference frame. So in other words, if the velocity of the box is close to the speed of light, then the experiments you perform inside that box will work the same as if the speed was close to zero. So it doesn't matter if you're moving very quickly or you're moving very slowly. But that's interesting because if the velocity of our room without windows, that we can't measure the absolute speed of, if the velocity of that room is close to the speed of light, then it seems like we have almost caught up to light. And therefore, experiments involving light might behave differently because we're almost moving as fast as light does. But that's not the case because you can't catch up to light. That falls into the ultimate speed limit we'll talk about in just a minute. You can't catch up to light. You can never go to the speed of light. Light will never appear to slow down relative to you, like catching up with a car on the highway. That's not how it works. Okay, so that means light, although it has a speed, can never be caught up to, and light will move at the same speed regardless how close you're moving to that speed. Okay. Well, that's fine. That would be covered under the second postulate, but we're going to have to think about the consequences of that, which we'll get to. But let's get on to the second postulate first. Okay, so the second postulate, very much following from the first one, as we were just talking about, states that the speed of light is the same in all reference frames, because otherwise, the laws of physics, they wouldn't be the same. Okay, if the speed of light wasn't the same in all reference frame, then the laws wouldn't be all the same. So if you state that the laws are all the same and perform experiments to prove that's the case, then you must acknowledge that the speed of light is the same in all reference frames. Now, it's not to say the universe had to be this way. We could have had the speed of light behave differently in different reference frames, but then we'd have different laws of physics, wouldn't we? Okay, so these are backed up by experimentation. Okay, so to continue with the Einstein's second postulate, we want to say that otherwise the first postulate could not be true. And that just calls back to the fact that I said one follows from the other. Okay, so that's it for the second postulate. Let's then state this idea of the ultimate speed of light. So the speed of light, a value that we have used before in previous lectures, is about 300 million meters per second. And in fact, we know that the speed of light can be derived from the permittivity and the permeability constant as an electromagnetic phenomenon. Right? So we've certainly seen where this number comes from in terms of its relationship to experimentally measured electromagnetic constants. But we also now are going to work with it in this context of the two postulates. Okay? So a consequence of the second postulate is that nothing can travel faster than the speed of light. So in addition to this idea that the speed of light is always the same, regardless in your reference frame, which implies you can't catch up with it, you also can't exceed it. Because again, that would mean different laws of physics in different reference frames. Okay, so that continues our little story, starting with the Michelson-Morley experiment, establishing the lack of an absolute reference frame, then having Einstein come along to propose a resolution to that, and then follow the threads, so to speak, of that resolution to their consequences on physics. Because although this made it so we could keep that there are universal laws in physics, right, including electromagnetic laws that they applied in the reference frame, that was maintained, the two postulates proposed by Einstein did come at a cost in a way, because they did force us to change some laws of physics, change our understanding of momentum, energy, simultaneity, time and space itself. So certainly there was some big consequences, and you can say that Einstein's genius was the ability to follow through and articulate what those consequences were, both in words and mathematically. Okay? So to talk about those consequences, we want to get a technical definition out of the way, and that's the idea of an event. Now, the reason that we're making a definition ruling like this is because what we have to do sometimes, other than work with some equations and make some arguments about how these theories reconcile themselves with classical theories in terms of approximations at low velocity, all stuff we're going to see. But we also have to do what are known as thought experiments. This helps with the understanding of relativity. There we go, close enough. So thought experiments require us to consider particular situations that may not, maybe a simplified version, but drive at the key laws that apply to these new modern physics. And in those thought experiments, one thing we have to make clear is what exactly we mean by an event. Okay, so the formal definition is an occurrence that happens in all reference frames. In other words, an event is irrefutable. Okay, events are not relative. So since we're talking about relativity, and we will, very much so in lecture 29, be talking about the relativity of space and time, okay, which is a very fascinating and difficult idea to understand at first, very different from our everyday experiences, as I said before. What we are never going to make relative are events. Because if events were relative, we'd live in a universe where there were lots of alternate timelines, maybe a universe with time travel. It's all sci-fi speculation. But the point is that events are irrefutable. They either happen or they don't. Okay? But again, that means that some things are relative. So for example, lightning striking a tree is an event. Okay? But let's consider that idea a little bit further and say 2 lightning strikes on one tree at the same instant is also an event. You might say, well, isn't it 2 events? No, sure, it's 2 lightning strikes, but since they're specified to strike at the exact same instant, it's just one event that's described this way. Events, some events require less description than others. Single lightning strike, single tree, 2 lightning strikes at the same time on one tree. Both events. Okay? Now, to further clarify that, let's consider a case that's not an event. So 2 lightning strikes striking 2 side-by-side trees at the same instant is not an event. In fact, it's 2 events, 2 separate events. Okay? And that's important because these 2 separate events are relative to each other. Okay? But don't take that at face value. Let's explore the idea with a thought experiment in just a moment. But let's first define exactly what we mean by the relativity of simultaneity. It's good to start with a definition, I believe, and then continue to elaborate on the idea. So it is often thought of, and I think of it as the first consequence of Einstein's 2 postulates. I would then follow with the ideas of time dilation, length contraction, which is the relativity of space and time, as further consequences. And then as we continue on, I would become more interested in other aspects of classical physics, including momentum and energy, and see how the postulates apply to those, kind of working our way through the classical laws of physics. Okay? But starting with the very nature of simultaneity is a natural starting point. And the relativity of simultaneity states that 2 events are simultaneous in one reference frame and are not simultaneous in another reference frame, moving relative to the first reference frame, that is. Okay? So the idea is if you have, 2 planets moving relative to each other, 2 events that happen as measured as simultaneous on one planet are not going to be simultaneous on another planet. All right? Because that planet is moving relative to the first planet. Now you might say, wait, that means we can never agree if 2 things happen at the same time or not. That is true. Often, however, if the velocities are not incredibly fast, if they're not close to that ultimate speed limit, then the effect is not noticeable. So only if the velocities of one of the reference frames where the events are being measured is very, very fast relative to the other reference frames, no discernible effects. It would fall within the bounds of measurability in whatever measurements are made. Okay? But we'll consider situations where we are moving very fast, right? Whether that's going to be futuristic spaceships or just, say, small particles like electrons and protons that naturally move very fast. But first, we're going to start with the prior category, the futuristic imaginary spaceship category. All right? So what we're going to do here, instead of doing any key equations or such, although there is one that I thought I had the speed of light, excuse me. But regardless, instead of doing any key equations or examples in this lecture, we're just going to do this single thought experiment. So let's go ahead and get started with essentially question 1. 2 supernovas labeled L and R occur on opposite sides of a galaxy at equal distances from the center. So here are the 2 supernovas. right? We're just calling them L and R. They were stars that just exploded, okay? The supernovas are seen at the same instant on a planet at rest in the center of the galaxy. So there's our planet, okay? It's at rest relative to the ship. Obviously, the planet is not at rest relative to some absolute reference frame because no such reference frame exists, okay? So a spaceship is entering the galaxy from the left at a speed of 0.999 c relative to the galaxy. And since it's relative to the galaxy and the planet was at rest relative to the galaxy, then we have our measurement. So the galaxy is acting like the absolute reference frame, but of course the galaxy itself is moving relative to other galaxies, okay? All right, but the main focus here is just going to be the ship and the planet. We're not gonna really be concerned with the galaxy at all, because we just need these two different observers. There are obviously people on the ship. The people on the ship are gonna be making measurements, and the people on the planet are gonna be making measurements. Measurements about the left and right supernovas. So let's get to it. So according to astronomers on the planet, were the two explosions simultaneous? Okay, so they occurred, right? They both occurred at the. They're going to be seen at the same instant. Okay, so the people on the planet see the two supernovas at the same instant. Now, just seeing two supernovas in the sky don't tell you that those two supernovas actually happened at the same time. Astronomers deal with that all the time because one supernova might be occurring in a very distant galaxy, another supernova might be occurring nearby in your own galaxy. So obviously there's different travel distances, and the fact that light travels at a certain rate means that they occurred at different times. But in this case, the distance or distances are equal, right? So we can say that yes, indeed, right? The stars are equal distance from the planet and the light arrives at the same time. Okay, now let's think about the spaceship. The crew on the spaceship, which supernova are they going to see first? Okay, again, this is meant to be a simple question, setting up for our thought experiment. Well, right, spaceship is coming from the left, which means they're going to see the left supernova first. The light wave from the left supernova is going to arrive at the ship first. Okay, so did the supernova that was seen first necessarily happen first in the rocket's frame? And that, of course, is the spaceship rocket, okay? So, is that a yes? No, definitely not. Since star L is closer, the light would just have taken less time to travel that distance and thus arrive at the ship. The people on the ship could definitely figure that out, right? They could use any number of techniques to actually know the distances to the left and right supernovas and know that the light just traveled less distance from the left supernova. So they know that it did not necessarily happen first. Okay? Okay. So then let's clarify where we're going to go with this by going back to our formal definition of an event. So is, in quotes here, two light flashes reach the planet at the same instant an event? Well, hopefully I've set you up to answer this question. So I think you should all be able to answer this question. Okay? Yes, definitely. A device like a circuit could be built that would only turn on if the two light sources arrived at the same time. Right? So you could build something that could only be triggered, and since that circuit would only be completed, and the circuit could do something like cause a buzzer to go off, then that buzzer ringing would either happen or not. There could be no disagreement between the crew on the spaceship and the astronomers on the planet between whether that buzzer went off or not. Okay, so that definitely means that because of the equal distance and the same arrival time at the planet, the people on the planet can definitively say that the left and right supernovas were simultaneous. Okay, so let's read this real fast. If you answered yes to part D, then the crew on the spaceship will also determine from their measurements that the light flashes reach the planet at the same instant. Okay, so there would definitely be an agreement about that. Experimenters in different reference frames may disagree about when and where an event occurs, but they all agree that it does occur. Okay, but we're not done. All right, so let's continue thinking about this and come at it from a slightly different angle. So we're going to look at the figure below, and this one shows the supernovas zoomed in a bit, and they're going to show them in the spaceship's reference frame with the assumption that the supernovas are simultaneous. The second half of the figure is a short time after the explosions, so this is proceeding in time, and we want to draw two circular wave fronts on that second lower figure, the second half of the figure, to show the light spreading out from each of the supernovas. Neither wavefront has yet reached the planet, that's kind of the scale we want to draw it at, and we want to be sure to consider the points on which the wavefronts are centered, right? So basically where the light originated from, and the wave speed of each wavefront, right? Because that speed is going to be, you guessed it, the speed of light. So go ahead and try to draw that. And I'll of course, draw it myself, but this is a good thing to make sure you can draw. Okay, so let's think about this then. We want to think about these spreading wavefronts like ripples in a pond. Essentially, the two supernovas would represent pebbles dropped in this pond, the galaxy, and then the energy would be spreading out, the light would be spreading out in a circular wavefront from that source, right? The two sources. Okay, so it would look like that. Okay, all right. Here we have the original star just before it blew up, right? We're going to assume simultaneous explosions, so they both blow up at the same time in the rocket's reference frame. Notice we're denoting the rocket's reference frame with a prime notation. So because we're calling the reference frame of the rocket S prime, that's its reference frame, okay? Notation we'll get more used to in lecture 29. All right, and then since the rocket is moving, okay, the rocket's moving towards the star, by the time the wave has spread out, well, the rocket has also moved a substantial amount, so it's closer to what is now the supernova remnant, right? The gases that are spreading out much slower than the light is spreading out, all right? So in most cases, this light would move much, much faster than the rocket. But here we have the rocket traveling at an appreciable speed of light. That's why we have this dramatic effect, right? Where it is noticeable that the rocket is actually starting to, get towards the wavefront, sort of catching up with it, right? Or at least, not having it spread many times faster than it. Okay? So again, notice where the wavefronts are centered. They're centered from where the supernova occurred, not from where the current remnants are located, because the ship has just moved closer to the remnants. That's why this distance has decreased, right? So this is the original distance between the supernova and the ship, and then this is just that decreased distance due to the velocity of the ship, right? Which is going to be, 0.999 c. Okay? All right, so notice some things about this figure. Notice that, of course, the planet has also got closer to the ship. Notice the planet's relative distance to the wavefront from the left supernova and the wavefront from the right supernova, okay? So according to your diagram, are the two wavefronts going to reach the planet, there's the planet, at the same instant of time? Well, what's the answer there? No, definitely not. The wavefront on the left will reach the planet first because the planet is moving towards that wavefront, right? Because it's moving towards the wavefront at the velocity of the reference frame of the ship, which is 0.99 c, 999 c, okay? Fine, that's what the figure tells us. However, does this answer to F conflict with our answer to part D? Right? We'll call your answer to part D, make sure you're clear on whether there is a conflict or not. Yeah, there is. There's definitely a conflict. Because in part D, we showed that there was an event of the two waves arriving simultaneously, an event that everyone had to agree upon because of the nature of the universe. Events either happen or they don't. The crew on the spaceship and the astronomers on the planet agree that the two waves reach at the same time. But we just showed that they didn't. Well, we showed that they didn't with an assumption, assuming that the two events of these simultaneous, quote unquote, explosions. Okay. So, continuing with the fact that we do have a conflict, what different assumption could you make about the supernovas in the rocket's frame that would bring your wavefront diagram into agreement with your answer to part D, the answer that there's an event of the two waves arriving simultaneously on the planet? Okay? So yes, okay? We could assume instead that the supernovas were not simultaneous in the reference frame of the rocket, because that would work. That would not conflict with our definition of an event being irrefutable, because that's two separate events. And all we're saying is that the two events occur simultaneously in the planet's reference frame, and they don't occur simultaneously in the rocket's reference frame. In fact, according to the spaceship crew's reference frame, which one would occur first? All right, it would no longer be simultaneous, and the supernova on the right would have to occur first, because only if the supernova on the right occurred first could the two wavefronts arrive at the planet at the same time, because this one would have to have a head start in order to catch up with the planet that is moving with relative velocity towards the rocket, okay, according to the rocket's reference frame. So there we have it. It is a strange result, But it does maintain the fact that an event either happens or it doesn't. But the strange part of it, is that, truly speaking, the two supernovas exploded at the same time in the planet's reference frame. Those two events happened. In this separate reference frame of the rocket, they didn't. They truly didn't. One happened first. It didn't just appear to happen first, it really did. So that tells us that time itself, the passage of time, is not absolute. The passage of time is relative, which is why we have the relativity of simultaneity. And we'll talk about the exact mathematical effect on the passage of time in moving reference frames in lecture 29. So I hope you can check out that lecture as well. I hope this one has been interesting and informative. Thank you so much for watching.